So, hello everyone, welcome back to your Comp 335 tutorial. Today we'll be looking at two fairly simple things, simplifying grammars, simplifying production rules of grammars, and then using those simplifications to convert your context-free grammar to normal forms, so either to Chomsky Normal Form, or we're also going to look at Greibach Normal Form, which is not something that we get to convert. And we're supposed to look at push-down automata, but I doubt very much that we'll get to cover it. So I've actually already posted an extra video for that. So if you just look at the lecture and tutorial recordings, there's already an extra video on push-down on PDAs. No, so you won't need, you'll never be asked to convert to a Greibach normal form because it's too difficult. We'll look at that later, but yeah, there's already a video on PDAs. So when this tutorial finishes, you can just look at that because I don't want to sort of stretch it. You can also like fast forward, make my voice go faster. So, but anyway, so production simplification. So the idea behind this section is essentially if you have a context-free grammar G that has some productions, what are ways to take those production rules and convert them, so convert all those production rules so that the converted equivalent grammar you have is not necessarily has less productions, but has sort of no redundancy, okay? So for instance, a bunch of lambda transitions, we consider that redundancy. And so we're going to look at how we can eliminate these and make our grammar simpler, not necessarily in the number of productions, but in its content. So the first thing we want to look at when it comes to grammar simplification is lambda productions and nullable variables. So what is a lambda production? Very simple. It's essentially when you have on the left-hand side a variable and on the right-hand side a empty string. So that's what we call a lambda production. Okay, and then we say that a variable is nullable if there exists a derivation from A to an empty string. So this can mean that A directly gives you lambda, or it could mean that A gives you B and that B gives you lambda. So this would also qualify for A giving you lambda. So then the idea is we have some lambda productions and we have some nullable variables in our grammar, and we want to essentially remove lambda productions and nullable variables and get an equivalent grammar that has none of those. So no lambda productions, and sort of by sort of consequence, no nullable variables. So this is a sort of simple procedure for doing so. There's a couple steps here. The first step is what you want to do is you want to identify all the nullable variables, which you're going to put inside a set Vn. So for instance, if you had A gives you lambda with any number of production rules and B gives you lambda, then in your set you would get AB. Okay, so this just helps you keep track of where the sort of algorithm is going. Okay, so then we have this initial grammar G, and we're converting it to one with no lambda productions G prime. So the first thing we're going to do is, except for all the lambda productions, we're essentially going to copy paste. We're going to copy paste all of the productions in G, so all of the productions P and G to G prime. So as long as this is not A gives you lambda, you're allowed to take this guy and essentially copy and paste it. So copy it, paste it to G prime. Okay, so that's the second step. So essentially what you have for now, so if you have your initial productions P, The copy pasted version you get is P prime. The only difference now is you have no, there are no sort of lambda productions, okay? But those lambda productions do give you some strings, and you essentially wanna maintain the information that that lambda production gives you. So how do you do that? Well, the idea is all of the variables here that you had identified in Vn, those are all variables that could be replaced by lambda, okay? So if, for example, I have a production A gives me, let me use S actually, S gives me little a, B. So I'm going to copy paste this into P prime. And then because I know that, let's say I know that A gives me lambda with some number of derivations and B gives me lambda with some number of derivations, then what I can do to conserve the presence of lambda without having it explicitly is I replace the variable by lambda, and I do that for every possible combination. So in this case, I could replace capital A with lambda, that would give me AB. I would replace B with lambda, that would give me AA. Or I could replace both with lambda, which would just give me A. The important thing to remember in this replacement is that you don't want to, so if this was instead S gives you AB, you don't want to also replace, like you don't want to replace both A and B by lambda, because that would give you a lambda production. So you want to replace, you want to do every possible combination of replacement except for the one that gives you lambda, because the goal is to remove lambda productions, okay? So that seems pretty abstract. Let's look at an example just to make it more concrete. So suppose I have the following context-free grammar G, which has these production rules, and my goal is to remove all lambda productions. So what do I need to do? Well, the first thing is I want to identify all my nullable variables. So I can do that sort of directly by looking at the lambda production. So I see that A gives me lambda, C gives me lambda. That means that A and C are nullable variables. But what I also need to notice is that B gives me C and C gives me lambda. So that means that B with a certain number of derivations gives me lambda. So I'm also going to include B in that set of nullable variables. Okay, so then the next thing you do, step 2, is you take this set of production rules, and apart from the lambda, so forget the lambda here, apart from the lambda, you're going to copy paste all of this, so all of these guys, to this set of productions. And sort of, if you observe carefully, that's what we're going to have. This guy is going to end up here, this guy is going to end up here, these two guys are going to end up here, and this is going to end up here. Okay. So far, I've copy pasted all my non-lambda productions. All right. So now, what's left for me to do is for each non-lambda production. So for instance, for this guy, I want to replace every nullable variable, and I want to do so with all the possible combinations, okay? So in this case, so that would be step 3. In this case, I've identified A, B, and C as nullable variables. They're all nullable. So then in the replacement combinations, I'm going to get sort of all the possible combinations with A, B, C. So what do I mean by that? Well, I could replace C with lambda and get little a, capital A, B. Or I could replace capital A with lambda and get little a, capital B, capital C. Because really this is just like A lambda BC, but putting a lambda does nothing. Okay. This is the same except you would replace capital B with lambda. And here you replace 2 of the 3 variables with lambda. And then finally, if you replace capital A, capital B, capital C with lambda, then you would just get the symbol A. Okay, and you essentially do that for all of the production rules that you copy pasted into this guy. Okay, so I do the same thing for capital B for BC. So I can either replace capital B with lambda, so that would be giving me C, or capital C with lambda, that would be giving me B. But I don't replace both B and C with lambda. Why? Because if I did that, then I would get a lambda transition. And what I'm trying to avoid, what I'm trying to remove, are lambda transitions. So there's no point in replacing both of them. Okay? And then you would do the same thing in B and C, but in this case, there are no extra production rules to create because, well, in this case, you only have symbols. And in this case, if you replace it with lambda, you would get a lambda, which would defy the removal of lambda transitions. So then once you finish that process, once you're done step 3, and this gives you an equivalent grammar G prime, such that G prime has no lambda transitions. So HD, what if it was supposed to be, yes, that would, yeah. So if you just had, so the question is, what if instead of C gives me C, I had C gives me lambda? Would I still remove that? Well, yeah, you would essentially remove this guy, and then you would essentially place you would replace the C as we just did before. So you would completely remove that production rule. And you should more or less see why it remains equivalent, because if I have something like C gives me lambda, and I didn't have this, so this was the only thing C gave me, then really going to C doesn't give me anything else but sort of allowing me to end the string. So if I remove this guy, and then I give myself all of the possible combinations, you should see that it sort of gives you, it doesn't give you any less strings and it doesn't give you any more strings. Yes, that's very good, actually. Yeah, that's a very good point, Ryan. So in actually, that I'm very happy you said that, because I forgot to mention it. In the examples we're going to consider that lambda is not part of the language generated by G. And this is so we don't have to have sort of picky cases in the sort of, so we don't have to make this procedure here more involved. But if you did have lambda gives you L of G, the only thing, so if you had this, then you would simplify your grammar, and then at the end, so only at the end, so you would do your process assuming this, and then at the end, because lambda is in G, then you would just add S gives you lambda, okay, and then that would keep it equivalent. But yeah, that's a very good point, Ryan. We'll also look at that later, so if it's not clear, don't worry about it. Okay, so that was for removing lambda transitions. The other thing we'd like to remove or get rid of is our unit productions. Unit productions are transitions, are sort of production rules that look like a single variable on the left and a single variable on the right. Okay, these are also a form of redundancy, because if I know that A gives me B, then why not just write directly what B gives me? Okay? And that's essentially the idea behind the following procedure, where you remove unit productions. So again, suppose you're given a grammar G with some unit productions, and you want to convert it to an equivalent grammar G prime without any unit productions. And again, the assumption here is that lambda does not belong in the language generated by G. Again, this is just to make everything more simple in the sort of pseudo algorithms we're presenting. So how do you remove all these unit productions and get to G prime? Well, the first thing you do is you remove any self productions. because you can clearly see that these don't give you any sort of new information. Okay. The next thing you do is you find all pairs of variables A, B, where from A you can, with any number of derivations, so with any number of derivations, you can get to B. Okay. So you store those variables somewhere. So for instance, maybe I have A, B, C. Well, for instance, that wouldn't work as well. For instance, I have A gives me B, and B gives me C. Let's say I identify all those transitions, and I store them because I'm going to use them in the next, well, in step 3. Okay. So then in step 2, what I do is I take all of the production rules P that are in G, except for the ones that are unit productions, and I copy paste them into P prime. Okay, so this is very similar to removing the lambda productions and then copy pasting the rest into P prime. It's essentially the same idea, except that here we're considering no unit productions. Okay, so we're copy pasting everything that's not a unit production. But of course, we know that these unit productions give us some kind of information. Okay, they give us some kind of information, so we want to conserve what they give us. So what we're going to do is once we have that set, so we have P prime, which contains all of the non-unit productions. So P prime is all of the non-unit productions. Then I go back and I look at my step 1, and I look at all the pairs of variables that give me, for instance, A gives me B, so all of the unit productions. And then what I do is, if in P prime, so it's important to notice that I'm saying P prime. So this is the set of production rules that has no unit productions. So if in that P prime, okay, if in this guy, I have the production rules, for example, B gives me x1 to xn, okay, and I know that A gives me with any number of derivations B. Then what I can do is to P prime, I can add A gives me, and then I directly go to x1 to xn. So essentially what I'm doing is I'm essentially skipping this guy, and I'm allowing myself to go directly from A to these sort of informative non-unit productions. And I'm going to take that and add it to P prime. And essentially I'm going to do that for every identified sort of unit production or unit derivation. Okay? And then once I'm done that, then I'm going to get a grammar G prime, which is equivalent to G but has no unit productions. So again, as any algorithm presented to you for the first time, it seems abstract. So let's look at an example to make this clear. There was actually a typo in the slides that I corrected, but for the purposes of this set of slides, just pretend that there is one in the slides, in the updated ones, but here there's a symbol B. Okay, but let's actually look at the example. So we're given a context-free grammar G with this set of production rules, and what I want to do is I want to remove all these unit productions. Okay, so remember the first step to doing that is I want to remove all of the self loops. So A giving me itself. In this case, if you look at the example sort of quickly, you see that there actually aren't any such cases. So this is already verified. Okay. The second thing we do is we need to identify all of the unit productions and unit derivations. So I can do them sort of step by step. So for instance, if I'm an S, I can directly get A, and I can directly get C. Okay. If I'm in A, I can directly get C. And if I'm in C, I can directly get B. Okay. But now what I need to be sort of careful about is I need to be careful because there's sort of a transition argument going on here. So if I'm in S and I read a C, then I can read that C and go to B. So I also have that S gives me B, and I have A gives me B. Okay, so I know that S gives me A, B, C, and I know that A gives me B, C, and I know that C gives me B. So these are the sort of stored unit productions that I'm going to use for, oh, this should be step 0 and this should be step 1 for step 3. Okay. So then step 2, what is step 2? Well, essentially I take all of the non-unit productions. So this is a non-unit production. These guys aren't unit productions, and these guys aren't unit productions. I copy that and I paste it in here. So I pasted this here, this here, this here, and this here. Okay. So then all that's left to do now is for each of these unit productions, I'm going to add to, so you can call this P prime. I'm going to add to P prime all of the sort of transitions that are implicitly given by these unit productions. So that's going to be step, so that was step 2, just copy pasting. That's going to be step 3. So I'm going to write the ones that I'm going to add, and then you're going to see that they're going to give you sort of this. Okay, so for S, what are the sort of productions that I need to add? So remember for now, these are the productions of interest because these give me non-unit productions. Okay, so if I'm in S, I know that I can directly get this, but I know that from S, so from S, I can give myself A, I can give myself B, and I can give myself C. So what I'm going to add to S, I'm going to add the production rules for A, the production rules for B, and the production rules for C. So the production rule for A's are going to be A and BC. So I'm going to add that to S. I'm also going to add the production rule for B. That's just, that's going to be S gives me B gives me little b, but now that's going to directly go to S gives me little b. And so you can see that this is again a kind of transition argument. The same thing for C. S is going to give me, thanks to C, it's going to give me little a, little b, capital A, and also variables C twice. Okay. So I'm going to take this and I'm going to add it to this guy. Okay. And did I make a mistake? No. Okay. So then this is what I get for S. Okay. And then I do the same thing for A. So for A, I know that from A, I can give myself B and I can give myself C in addition to this guy. So that's what I'm going to do. I'm going to add the production rule for B, for capital B, that's this guy. And I'm going to add the production rule for capital C, which are these guys. Okay, so I'm going to give myself little a, little b, capital A, and CC. Okay, and I'm going to add, so I'm going to add this guy to sort of the highlighted production rules, and that's going to give me my full set of production rules for A. Okay. For B, there isn't any transitions for B, so I can just go to the next one. The last one I have is C. So if I'm in C, I can get sort of my own production rules, but I can also get the production rules of B. Okay, and so to this thing highlighted in yellow, I'm also going to add C gives me what capital B gives me and what capital B gives me is a little b. So I'm going to take this guy and add it here. So we see that this is added here. Okay. And once you're done step 3, then you've gotten a equivalent grammar G prime that has no unit productions. And you can sort of verify that there isn't any sort of single variable on the left and single variable on the right. Okay, so we can see that we've actually done the sort of process correct. Okay, so that's the second type of simplification you need to do. The last one is removing what are known as useless variables and also useless productions. Useless productions. Okay. So, well, first of all, what is a useful variable? A useful variable is a variable that appears in at least one derivation of a string of terminals. So if for instance, if I want to say that A is useful, so is A useful? For A to be useful, I would need to start at S, and then I would need to see somewhere A occur in a derivation, which would allow me to get a string, let's say x1 to xn, where the strings are only of terminals. Okay, so if A takes part of that kind of derivation, a derivation that actually gives you a string, then it's useful. Okay, and then otherwise, so if the variable is not useful, the variable is very naturally called useless. But if you don't want to sort of go through that process of checking if A is in any derivations, you can also think as a variable being useless if it is either unreachable, meaning that, so if, for instance, B is unreachable, that means that there are no paths or there are no derivations from S to B. So there are none. Okay, there does not exist any derivation that goes to the variable B. Or to be useless, it could also be non-generating. So non-generating would mean that there are no, so essentially, if you want to say C is non-generating if it never, so it never gives you a string of terminals. So it never gives you a string of terminals. Okay, so so then you can sort of see why we would call a variable like that useless, because either you can't even get to it, or if you do get to it, it never produces a string. So it never contributes to the strings generated by the grammar. And so very naturally, if you sort of extend this definition to productions, and you say that a production is useless if any, so if its left-hand side or its right-hand side contains a useless variable. So if you take all of those useless productions and you remove them, so removing those useless productions does not modify what strings are accepted by G. So if you remove those useless productions, you get an equivalent grammar G prime, okay? And the last type of simplifications is going to be just that. It's going to be removing useless variables and useless productions by consequence, okay? So how do we do that? Well, let's look at an example. Suppose we have the following production rules in our grammar G, in our context-free grammar G, and we want to remove all the useless productions. So remember, it's useless if it's unreachable, unreachable, or if it's okay, let me just write non-generating for non-generating, okay? So there's actually a nice trick that you can use for unreachable variables. you can use what's called, what's known as a dependency graph. This isn't actually in the slides, it's just kind of an FYI. And what is a dependency graph? It's similar to kind of a graph you would see in an FA, but very sort of bare bones. So a dependency graph works as follows. So you're trying to convert your set of production rules to a transition graph. So you're always going to start in your variable S. And then I wanna use this graph to tell me which variables are not reachable. So what that means is there's going to be a transition from, let's say, a variable S to a variable A if there is a production rule that contains A on the right-hand side. So for instance, I have capital A on the right-hand side and an S on the left-hand side, okay? But it could have easily been something like A, capital A. That would still mean that A is reachable from S. So if A is reachable from S, that means that from S I can go to A. So I draw an arrow to A or an edge to A. The same thing for C. So I create another vertex C and I draw a directed edge from S to C because I can reach C from S. Okay, so very natural kind of production rule conversion. And then if I'm in A, I can reach myself, so I could just self loop there. If I'm in C, I have a C on the right, so I can reach myself, and I can also reach A. But what we can notice, thanks to this dependency graph, is B is all alone here, and it can never be reached. So even though B can go to A, there isn't any directed graph that goes into B. There isn't any directed edge that goes into B. So B is going to be unreachable because it can never be no derivation can get to B, to capital B, starting from S. Okay, so we can sort of automatically just remove that production rule B and any other production rule that would contain the variable B. Okay. So we see that that's actually the only unreachable variable. Next, for non-generating variables. So a trick to sort of seeing if a variable is non-generating is, first of all, if the variable has a production rule with some terminals with only terminals on the right-hand side, then it's already generating because it can already sort of generate some terminals at some point. So for instance, if I'm in A, I can sort of loop in A, but then at some point I can stop that looping and use this lambda to get an actual string out of my A, okay? The same thing, the sort of a transitive argument can be said for S. So if I'm in S, so for instance, if I'm in S, I can choose to go to A. And then if I'm in A, I can, let's say I produce one A, and then from that I use a lambda. So I see that from capital S, I can get a string of terminals, in this case just A. So I see that S is also generating. So S is generating and A is generating. Let me just clean this up a bit. Okay. However, if I'm in C, what's going to happen essentially is if I'm in C, then I have to replace C by A, C, or A, capital C, capital A. Then I can, let's say I just replace the capital A by lambda. So I replace the capital A by lambda. So I get AC, okay? But now I can't get, you can sort of see that I can't get to a production rule that's only going to give me terminals. Because again, I have C here, and then capital C, the only thing I can replace it with is this guy. So I'm going to again replace it with that guy, okay? And then even if I replace the A with a lambda right away, I'm still going to be stuck with capital C. So I see that in fact, even if I run this program forever, if I'm in C, I can never give myself a string of terminals. Okay, so that means that C is non-generating. So I can automatically remove C. Okay, and not only can I remove that production rule, but I can also remove any production rule that contains C on the right-hand side. So S gives me C, can be deleted here, and the simplified grammar that has no useless productions is going to be this guy. Okay, so this is the equivalent grammar G prime, where G prime has no useless productions. Okay, so what was sort of the point of showing you these three types of methods, removing lambda productions, unit productions, and useless productions? So the point is, if you're given a grammar and you're given the task to clean up or simplify the grammar, to completely simplify a grammar, you need to do all of the three steps we just sort of looked at. But what's important to remember is the order in which you simplify is extremely important. So I can't stress that enough. This is like a double star. It's crucial, because if you don't follow this order here, where the first thing you do is you remove lambda productions, the second thing you do is you remove unit productions, and the third thing you do is remove useless productions. If you don't follow that order, okay, then what could happen is you could end up at the end with a grammar that maybe still contains a unit production, or maybe still contains a lambda production. So it's very important to respect this order. This is in fact the unique order that gives you that always gives you a simplified grammar with no lambda productions, no unit productions, and no useless productions. Okay, so all right, so now maybe an exercise for you, so maybe ignore what's on the right of the screen. Okay, how are we doing on time? Okay, very bad. All right, so okay, I'm still going to give you maybe a chance to think about what you would do. So maybe take let's say 1 minute. That's generous. Take some time and we'll go over the sort of question together. Okay, so it's been maybe 50-ish seconds. So hopefully you've at least looked at the grammar and you've remembered what the steps to simplifying this grammar are. Okay, so because it would have taken a lot of time for me to just sort of write all the steps, I gave myself a bit of help here and I added some intermediate steps. But let's sort of go over the solution together. So remember, what is the first thing you need to do when you simplify a grammar? You're going to want to remove lambda production. Okay. So when you want to remove lambda productions, you need to identify the set of nullable variables. Okay. So what are the set of nullable variables here? Well, I see that, so let me write it here. I see that A directly gives me lambda, so I can put capital A here. Then I see that D directly gives me lambda, so I can also put that there. But then I can use a transitive argument and say that if I'm in D, then I can go to D, and then from D, I can give myself a lambda, okay? So that would mean that B is nullable, and if B is nullable, then C gives me B, that's also going to be nullable. So so in fact, A, B, C, and D are all nullable variables, okay? So I've identified those, so I guess this is like 1.1. Then the second thing you would do, right? The second thing you would do is, except for the lambda productions, so except for this guy and this guy, you would copy paste this grammar into one that has no lambda productions. So let's see if I did that correctly. So S, I have this. So S, I have this guy, and this guy, okay? Then for A, I have capital A, little a, capital A. And for B, I preserve these guys. For C, I preserve this. And for D, I preserve this, okay? So that's step 2. Step 2 is done. Then remember the last step, step 3, is I do the sort of all possible combinations of replacements, okay? So let me pan out a bit. So for instance, how did I get the additional productions here? Okay, so what I did is I added all the possible replacements. So I'm an S. So what are the possible replacements? Well, it could be I have 2 little a's capital A, and I replace this capital A by lambda. So I would add S gives me little a, or I could also replace this capital B, so this capital B by a lambda, and get A capital B, or I could replace both and get just little a, okay? Then I would do the same thing for DAB. So for DAB, I could replace D with lambda and I would get AB, or I could replace capital B with lambda and get DA, or I could replace both with lambda and get A. Okay. Yes, I know. I'm almost there. So now that I have this, what I'm going to do is I'm going to take these guys and add them to this set of production rules. Okay. And as Simon pointed out, there are some production rules that are going to be repeated. Okay. But what's important is sort of try not to get confused with that idea when you're doing this. Okay, try to do it robotically, mechanically, and then once you've added, then you can eliminate duplicates. So for instance, AB, so I'm going to remove it here. AB is a duplicate, and also little a is a duplicate. So I would remove that guy. Okay, and so then the non-lambda productions, the set of non-lambda productions from S would be sort of all of these guys, okay? And then the same idea for sort of capital A. I know that A, B, C, D are all nullable variables. So for this guy, I could replace the capital A on the left-hand side with lambda. That would give me, so let me write it here, add. So I would have to add little a, capital A. I could also add, if I replace the right capital A with lambda, I would get capital A. Or I could also replace both, which would mean I would get little a. And that's all I would get, okay? So I would take this and then add it, and then I would get this set of production rules, okay? In this case, I have no repetitions, so that's fine. And then I think, well, hopefully you see the sort of idea by now. So for instance, this guy, B, capital B, you could replace the capital B with a lambda. The D, however, this capital D, you would not replace with a lambda, because if you did, then you would get something like B gives me lambda. Remember, the whole point of this initial process is to get rid of lambdas So you would not do that. So you would not do that. And let me just erase it so it doesn't look like I cancel it out. Okay. And then for C, C gives me B. There's nothing to replace there because, again, I would get a lambda if I did. And then for D, if I replace this capital D, then I would just get VA. Okay. So this is after step 1. So after the removal of lambda productions, this is what I would get sort of as a result. Okay. So what's the next step? The next step, or where can I write this? So I'm going to just write it. The next step is to remove all the unit productions. Okay. So I need to, first of all, identify all the unit productions. So what are they? Well, in this case, I think I made it easier for myself and for you. It looks like the only unit productions, so the unit productions are C gives me B directly, and B gives me D directly. And by sort of transitivity, I also have that C gives me D with any number of productions. Okay, so these are the unit productions that I sort of store. What you also need to notice is, so that was step 1 in the sort of removing of unit productions. The initial step was remove any self variables, so self production rules. So in this case, there aren't any, so this is already done. Okay. 2, 1, I identified the unit productions. Then the second thing I need to do is I copy the non-unit productions and paste into P prime. So P prime is essentially this guy. Okay. So essentially I just copy paste all of this. So let me I copy paste all of this into there, except for C gives me B and B gives me D. So I don't have that. Okay. And you can see that for S, A, and D, so for S, A, and D, I in fact have the same, I have exactly copy pasted the same productions. The only ones that are different, and that I'll show you why they're different, are B and C. For now, you can think of sort of initially what you have is you just have B gives you little b, capital B, little b, and you have C gives you, and you have essentially nothing. Okay, so this is like the intermediate step that's going to, so this is like the final. This is, I feel like this is a bit confusing, but this is like the intermediate step. Okay, well, let me try to clean this up. Yeah, so this is like the intermediate step, and then once you do the copy pasting of these guys, you're going to get to a final production rule. Okay, so let's do that. So I know that I know B gives me these guys, but I also know that B is going to give me the stuff that D gives me, and the stuff that D gives me is this stuff. So to B, I'm also going to add BDA, and I'm also going to add BA. Okay, and then what am I going to add to C? Well, to C, I'm actually going to add all of the non-unit productions, right? So I know that C gives me D, okay, and I know that C gives me B. So one thing that you could do is you could just immediately take this and paste it there, or you could do it sort of step by step. So you could do, I know that C gives me a B, and this B was the one before I added the green stuff. So the B was essentially just this. So then C would give me this using red, this guy. And then also C would give me the stuff that D gives me, okay? And that would be this stuff. Okay? So then I would also add BDA, BA. Okay. So this would be, whoops, what did I erase? This. So this would be the production rules that you would now add to this guy, and that's what allows you to get these two production rules. Okay. In fact, you can actually see that they're mirror images of each other, which stems from the fact that C gives me P. Okay. So there are no unit productions anymore. So I've completed removing unit productions. The last thing I need to do is I need to remove useless productions. So remember, a production is useless if it is either unreachable or non-generating. So what are the unreachable variables in this case? Well, I use the sort of same idea with the graph, with the dependency graph. So I start in S. I can see that from S, I can go to A, I can also go to B, and I can also go to D. So I can go to A, and B, and D. Okay. Then from A, let me use a different color. From A, I can only go to myself. So from A, I can only go to myself. If I'm in B, I can go to either myself or D. So I can go to myself or D. I'm going to skip C for now, and then if I'm in D, then I can only go to myself. So there's a reason why I skipped C, obviously. The reason why is if I draw C, I see that I observe that if I'm in C, I can go to B, and I can also go to D, but there isn't any incoming or there isn't any incoming directed edge that goes into C. Okay, what does that mean? Well, hopefully you're all telling yourself that that means that C is unreachable. C is unreachable, so that means that I can immediately delete. C from the sort of production rules, and that's in fact the only unreachable state that I'm going to delete. Okay. The other criteria is I want to remove all the non-generating production rules. What are those? Well, you could start at variable S. So remember, the trick is if you see that your variable on the right-hand side only gives you terminals, then for sure it's generating because it generates at least that terminal. So if I'm in S, I can give myself AA. So S is generating. If I'm in A, I can give myself little a. A is generating. If I'm in B, I can give myself little b. B is generating. If I'm in D, I can give myself PA. D is also generating. So they are all generating. And this is in fact the final simplified context-free grammar, which is in fact equivalent, meaning it generates the same language as the initial, so as this initial grammar G. So again, it doesn't look like it's simpler. It actually looks a lot more complicated, but it's simpler in the sort of idea that it's less redundant. There are no or very few redundancies here. Okay, and that, yes, okay, and that finishes the section on simplifying grammars. Okay. So as suspected, I'm not going to have time for PDAs, but I will have time for normal forms. So there are two important types of normal forms that you're going to see in 335, well, that you've seen already actually in 335. There's Chomsky normal form and there's Greibach normal form. Okay? So let's look at both of these sort of individually. What is a Chomsky normal form? Chomsky normal form, a context-free grammar G, is said to be in Chomsky normal form if all of the productions are of the form a single variable on the left, so a single variable on the left, and then exactly two variables on the right, or a single variable on the left and a symbol on the right. Okay. So if all the production rules look like this, then you can say it's in Chomsky normal form. By the way, if you're curious, Chomsky is actually a linguist known as, you probably don't care, but I thought it was interesting. His name is Noam Chomsky, and he's actually still alive. So he's one of the very few people in sort of my memory whose theorem or whose definition is named after a person that's still alive. I think that's pretty cool. But let's get back to the example. So I have an example here of a context-free grammar G. Okay, and I'm claiming that this context-free grammar is not in Chomsky normal form. For it to not be in Chomsky normal form, at least one of the production rules cannot look like both this and this. Okay, and we see very easily that very immediately that S gives me the variable A is a production rule that sort of breaks Chomsky normal form and allows me to claim that it is not in CNF. Okay, but what we're interested in is if, for example, we have this context-free grammar G, can we convert it to a grammar that is in equivalent grammar that is in Chomsky normal form? That is the question. And in fact, the answer is yes. For any context-free grammar G, where the language generated by G does not contain the empty string, this is again because lambda not in L of G is because we want the sort of steps to be fairly straightforward, and the procedure sort of gets a bit tricky if you allow lambdas. Okay, so the theorem says that if you're given any CFG with this characteristic, then you can convert it to a equivalent grammar G prime, which is in Chomsky normal form. Okay, so what are the steps to do that? Well, the first step you need to do is you need to simplify G. Okay, so all that simplification wasn't for nothing. If you want to get a Chomsky normal form equivalent grammar, you first need to start with a simplification of G. Okay, so you simplify G, and that gives you your initial production rules P prime. Okay, then the next thing you need to do is you identify all of the terminals in T. So for example, they could be A, B, C. And for each terminal, you reserve a production rule for that terminal, which you could denote. This is similar to the notation in your slides. T of X, so for instance, T of A, gives you the symbol, the symbol A. And we see that this production rule looks like this production rule, which would maintain a CNF. Okay. So you do that, and you add all of those productions to P prime. And the other thing you do, which I didn't mention here, is every production rule. So for instance, if I have the production rule X gives me A capital B little c, I convert this to, I essentially convert the symbol to the variable. So I convert the symbol A to TA, then the variable B stays the same, and the symbol C to TC. Okay, so now I get production rules that look like this. And as you can see, this is not yet in Chomsky normal form because you need to have exactly two variables on the right-hand side. How are you going to manage to get there? Well, for instance, suppose you have n variables on the right-hand side. What you can do is you reserve the first variable on the left as the sort of variable that you're going to keep for A, and then all the other variables V1, you call those V1, okay? And then those are going to go to another set of production rules. So you can think of this as, maybe this is the sort of final form, but you can think of this as doing A gives you C1, V1, and then V1 gives you C2 to Cn. Then you do the same thing, the same process. You take this guy, you call this a V2, and then V2 becomes C3 to Cn, okay? And then again, you do the same thing. This can be called V3, and then I hope you can see where this is sort of going. You get C4, V4, and you keep that process going until you get Vn minus 2, Cn minus 2, Cn. So you have the last two, what am I saying? The last two variables in the last productional, okay? And you need to do that for every, so it shouldn't say for any, it should say for every, so think of this as a for loop on all of the production rules. For all of those production rules, A to C1, Cn, you convert them. So as you can see, this can become a very lengthy process. And so that's why for the exercise to illustrate this example, I've chosen a non-lengthy example, okay? So I have the following, okay, I can't really give you any time to do it. Well, so I'll do it with you. So I have the following grammar, grammar G, I want to convert it to Chomsky normal form. So I have this grammar here. The first step is going to be to simplify it. So remember, remove the lambda-productions, then remove the unit productions, then remove the useless productions. So I'm not going to do that because obviously that takes a lot of time. It's going to, if you simplify that, it's directly going to give me this. But what I am going to do is the steps after that, okay? So remember, the next step is you take all of the terminals, and for each of the terminals, you give them a productional. So in this case, I only have two terminals, A, B. So I have, let me do it right. I have TA gives me A, and TB gives me B. And then what I'm going to do is I'm going to modify this grammar, and for each symbol, I'm going to replace it with the variable. So, okay, so this is going to be TB S, and then this is going to be TA. I'm not gonna change this one though, because this is already S gives me A, and that doesn't violate Chomsky normal form. So I'm going to keep that one. But then for AAB, I'm going to convert that to TA, TB, and the same thing happens for A. Okay. So now I've essentially completed step 2. Now I need to do step 3. Okay. So what is step 3? For step 3, I need to take all of the production rules that don't respect Chomsky normal form and make them pairs of variables. Okay. So how do I do that? Well, I see here that this is 3 variables. So what I'm going to do is I'm going to take TA, TB and make that V1, and then make V1 give me the TA, TB. Okay. So instead of TA, TB here, I'm going to have V1, and the same thing is going to happen here. I'm going to have TA and V1. Okay. And then you can see now that we've actually gotten a equivalent grammar G, which is in Chomsky normal form. Okay. And then at this point, TA, V1, yeah, you could also do that. Yeah, for sure. So you could also do, it doesn't, as long as you respect, if you use that logic, as long as you respect this logic as well. So then you would need to, so for example, if you had C1, C2, C3, C4, and then let's say you said this was V1, so V1 would be C1, C2. So then it's not as sort of direct, because then you would get V1 is C1, C2, so then you would get V1, C3, C4, and then you need to do the same thing. You need to say this gives you sort of Well, I guess, I don't know, I'm a bit confused by my own. Basically, what I'm trying to say is be careful if you try to use a different order, because this order is sort of proven to always work and it's fairly mechanical, so it's pretty safe. But yes, Bowen, you could also have used TA in that case, okay? As long as it respects the, as long as it keeps the sort of grammar equivalent. And yes, exactly, C, I'm going to call you C. The last thing I was going to say is we assumed for this simplification method, we assumed that lambda was not in L of G, okay? But the last thing you sort of, so for this guy is in Chomsky normal form, okay? So really, it was probably a mistake in the example because there shouldn't have been a lambda that you would get from G, but in this case there is. So you can get the next best thing to Chomsky normal form. Next best thing to Chomsky normal form is as C sort of observed. In this case, if I'm in S, I can go to A and then I can get a lambda. So in fact, this assumption is incorrect. Lambda is an L of G. So what I can do to keep my grammar still simple, but now no longer in Chomsky normal form, I can add S gives me lambda, okay? So this is no longer in Chomsky normal form, but it's very close to being there. And we can sort of call this a pseudo CNF, okay? Yeah, so the reason why it's for all practical purposes is because the only thing that would sort of make a difference is you would have to add this S gives you lambda. But you always know that you can add S gives you lambda. So as you said, sort of for the purposes of simple algorithms, you sort of make this assumption. Okay? But in this case, lambda is in the grammar, in the language accepted by G. So to keep it equivalent, to keep these equivalent, you would have had to keep lambda. Okay? But maybe if I go back to, like, what you need to notice is this A here belongs to the terminal string. So that means that A cannot be lambda. Okay. So strictly speaking, if you want to be in pure CNF, you can't have a lambda transition, and that's why you assume lambda not in L of G. But for practical purposes, you can always add that lambda. Okay. All right. So I hope that was clear. Okay. Let me answer those questions right after I finish. This is the last slide, so I'll do that. The last slide is about Greibach normal form. I don't know if Greibach is still alive. You might want to check that. And so we say that a context-free grammar G is in GNF. Is in GNF if all of the productions have the form a single variable on the left and then a single symbol on the right, followed by any number of variables after that symbol. Okay. So for instance, if you had S gives you little a or little ab, and then B gives you little a, let's say B, then this would be, or let's say, yeah, let's say BB, this would be in Greibach normal. This grammar here is not in Greibach normal form because, for example, if you're in variable S, then you read the symbol A, and then right after that, you should only see variables. But in this case, you see terminals and variables. Okay. And so, as I said, we're not going to discuss a conversion algorithm, but there's a theorem here that tells us that every context-free grammar G, where lambda is not in the language generated by G, okay, every such grammar can be converted into an equivalent grammar G prime in Greibach normal form. Okay, and one of the reasons why I actually decided to include this is because this might be, so I don't know if it might be, but it could be helpful to solve assignment 3, question 2. I think it's question 2. I'm not going to say anything else, but I'm saying that it's possible that you might need to use this theorem to help yourself prove what they're asking. Okay, so I'm not going to answer any questions about that. I know there's going to be questions. I'm not going to answer. That's the only hint I can give you. Okay, doing anything else would essentially just give you the answer. Okay, so for anyone who needs to go, that essentially